The next part of this video is on transformers. Transformers look basically like this, as you can see from the PowerPoint slides. Transformers, just writing it out. Basically, it's an iron core. It could even be a nail, where you have one coil of wire wrapped with a certain number of times N1 I should say, and then another coil of wire wrapped around with a different number of times, in this case N2. You can see in this case that N2 is greater than N1. It's not always that way, it could be the other way around. But what happens is you have an AC voltage that's put on this side of the transformer, and that AC voltage, keep in mind you're going to have a current going this way, then a current changing direction and coming back. It's going to keep changing direction at a frequency given by whatever frequency of the generator there is, and that changing current is going to generate a flux through this coil, and there's also voltage to this coil, changing voltage and AC voltage as well. And as it changes, that flux changes and it creates a magnetic field through this iron core here that this other one also has access to. This other number of coils, experiences that changing magnetic field and sets up its own AC currents as a result of the changing flux in here, as a result of Faraday's law. So this one here generates a magnetic field, which transfers through this iron core to this one, which comes back and generates a current and a voltage through this coil here. Now it turns out that whichever coil has more turns in it is going to be the one that has a greater voltage across it, because when there's more turns, remember the flux generated by this one is generated by however many turns there are here. If there's more here, it's going to be effectively a greater change in flux, or greater N in that N times B times A equation, which is going to result in a larger voltage here. If there's a larger voltage here than here, well, you can't have a larger current and a larger voltage over here, because then you'll be generating power, which is impossible. So if there's a larger voltage here, it means there's a smaller current here than there is here. So these transformers are ways of changing the size of the voltage and the current that passes through different circuits. That's what a transformer does. And in subsequent videos, I'll show you how that voltage changes, but it's basically a function of the ratio of the turns N2 to N1. In this case, if you have a voltage, for instance, of 2 volts here, of AC voltage of 2 volts, and you have twice the number of coils here, then you'll have 4 volts here, but half the AC current that was passing through here as compared to here. So it's really a way of getting, one way to think about it is the way of getting the voltage in this coil to another coil, but it's going to be a different voltage. But you're able to transfer through this metal ring and change what the voltage level is. Isn't that amazing that we can do that? And there's reasons for that I'll describe in a subsequent video, and that I also describe in the PowerPoint slides. And the other thing that this is, you might have seen this, an example of this working, is if you have an electric toothbrush that charges on a charger, but there's no connector, there's no wires. You actually have a coil of wire here and a coil of wire there. They share the same flux, so when this one varies, this one picks it up, and it's able to charge a battery from that. And so without actually having physical electrical contacts, you're able to generate power over here, which is great because contacts can wear out. There's opportunity when you have contacts that they can get corroded, all sorts of things. That doesn't happen in this situation here. More in a subsequent video. So when we think about the transformer, I'm going to say that the primary has a voltage V1 across it. The secondary has a voltage V2 across it. And if you apply Faraday's laws and the laws for the generation of current and voltage in a transformer, you would end up with this relationship here. I'm not going to step you through the derivation right now, but basically says that the voltage on the right-hand side divided by the number of coils on the right-hand side is equal to the voltage on the left-hand side divided by the number of coils on the left-hand side. That's what this equation is telling us. The result of that is V2 is equal to N2 over N1 times V1. And this is the transformer equation that can be used to determine the voltages on the two sides of the transformer. Alright, this is the equation for the voltage at the secondary coil of the transformer and how it relates to the voltage at the first coil of the transformer. Basically take that AC voltage multiply it times the ratio of the two numbers of the coils in the secondary and primary coil of the transformer, and you get your secondary voltage here. So how do we relate that to current? Does the current also increase if the voltage increases? And as I mentioned, it can't, because power at best is going to stay the same. The power of the secondary at best is going to be equal to the power of the primary. In practice, you might be more like at 95% because you always have some loss in your system. Remember from earlier in the semester that the power of a circuit is equal to the current passing through the circuit elements times the voltage across the circuit elements. So we saw that earlier in the semester. So if we apply that to the transformer, let's just look at the best case. Let's say all of the power of the primary is going to be delivered to the secondary. If that's the case, well, we can say then that the current at the secondary times the voltage at the secondary is equal to the current at the primary times the voltage at the primary. Again, the primary and the secondary are this. There's the primary, there's the secondary. Everything with a 2 is a secondary. Everything with a 1 is a primary. This is where your load is, and this is where your power supply is, your AC power supply. All right, if that's the case, then we can say, well, this product has to be, these two have to be equal to each other because the power in the secondary has to be equal to the primary power in the primary. We also know this equation for the voltage in the secondary coils of the transformer and how it relates to the voltage in the primary coils of the transformer times the ratio of the coils. If I plug that into this equation, wherever I see a V2, substitute N2 divided by N1 times V1, and then I solve for I2, first thing I'm going to do is cancel the voltages V1 on both sides of the equation. Those both cancel. Then I solve for I2. Okay, say I2 it's going to be equal to N1 over N2 times I1. Notice this is the opposite of the other case. For V2, I had V2 is equal to N2 over N1 times V1. What this is saying is that if the voltage is increased, the current is going to be decreased. So if the voltage doubles, the current's going to be halved. If the voltage increases by a factor of 4, current's going to decrease by a factor of 4. Why would we want to do this? As I also describe in the PowerPoint slides, when you have transmission lines and they're transmitting energy over very long distances, you want the current in those lines to be really low. And a transformer can make that happen. So that's why in those really long distance transformer lines where you get wires sending energy through hundreds of miles across the country, you're going to have really high voltages because you're stepping up the voltage, but you're stepping down the current. And that allows for less loss on the transmission lines, so that you need transformers from the point where the power supplies, the turbines and all that, are providing energy to the grid. There's transformers to make that energy be at high voltage and a really low current. On the other end of the wire, we have transformers that drop the voltage back down and bring the current back up. You have them all the way between the pole and your house. You have smaller transformers, but there's transformers at different points along the electric grid. So it's a really useful application of what we've been talking about. It's applying Faraday's law, basically, to electric circuits in a really practical fashion.